Okay, perfect. This is the presentation about the environmental application. Of course, I want to thank all my team because you can imagine it's a huge work and can be only shared between our group of people. And this is the outline of this presentation. This presentation is very long in terms of slides. It's not intended to be served here now in this fashion. And of course, the presentation will be released to the project for full dissemination. And this presentation is designed to be basically half a day seminar with half a day of a tutorial. All the tutorials are on the repositories.
We are not going to give you more time.
No, it's something that users can do even by themselves on their machine or our machine. It's pretty tactical stuff. Okay, let's introduce the environmental application. It's kind of digital twin, but you know, digital twin is a buzzword. This is something that is really working. These are the products that we want from the environmental application. We finally we need to trace. I say here inerts because I can't say marine pollutants because otherwise people are scared. Touristic operators in the Campania region are scared, so I don't want to. I want to be wake up tomorrow, so it's better if I use the technical term of inerts. That we will see in the description of the model. That means we model particles that don't interact each other. To trace, or better, to calculate transport and diffusion of these particles, we need to know the flow of the sea currents and a really high resolution fashion. That means, kilometers are too much. We work on 140 meters and we want to do more, and maybe this could be next project, I don't know. And to move the sea currents, we need basically, we need the results of another model, and we don't know these results from the Copernicus European project, but even we need really high weather forecast, really high resolution weather forecast, and that means we need to run our model. Our model, of course, is a community model. So this is the main workflow of the application. We can see how we download data from the US and SEP, or if we want to perform a scenario analysis, we use European ACMWF data. Please don't ask me why this during the presentation. I will talk here about this offline. We use the weather forecast, weather research forecast model is widely used. There is a community model. We have configured this model in the way we produce a final land resolution of 1 kilometer. That actually is one of the highest resolution in the Italian scenario till now. For operational models, of course. As you can see from the workflow, the results from the weather forecast model are used to drive the ocean model. We use ROM's ocean model. It's another community model widely used. And finally, we use these results to drive Wacom. Wacom is the model that basically we developed from scratch during the ADMIRE project. Now we have to take note about this. WRF and ROMs are community models, are open source, but basically we must consider this as legacy software. This is already stated in during this user day. It's important because it means we can even modify and compile the software, but our modification will never accept, or it's really difficult, it will be accepted in the main branch development. So if we don't touch the code, it's better. And this is the common philosophy of all this approach of making ADMIRE compliant environmental application. Now the building blocks of the environmental application that I will really fly on it because are something that we use as is. The WRF is the first component. Actually, WRF is a sub-workflow that have to be assembled in to have the data we need for the other steps. Actually, the only notable thing here is we produce data on three domains: the let's say Europe, Italy, and Campania and south of Italy, increasing the resolution with a rate of 1:5. Basically, we have 25 kilometers on the Europe, 5 kilometers on Italy, and 1 kilometer on the south of Italy. We produce 7 days, and basically we perform 7 different simulations. We stop the simulation, save the status, and then we restart. In this way, we produce a kind of stream of simulation. Already we saw that an interaction with the Capio in a different configuration carry out almost immediately output for humans. In this means pictures, maps, weather maps. While in this case, we need to wait for the whole simulation to have enough data to run ROMs. And this is an example of input and output with the sides of each stage. This is ROMs. ROMs means data from the Copernicus project and data from the high resolution weather forecast. The results will be used by Wacom. And this is an example of the input and the output. And the sides of the storage means the final destination of data produced and the Scratch directory. It's very important to evaluate the size of the Scratch directory because in workflow, it's the exchange between tasks is critical. And during this day, we saw many ways to approach this in a really smart way. Now it's the time of Wacom. Wacom was developed from scratch. It's a highly scalable, high-performance Lagrangian transport and diffusion model for marine pollution assessment. Okay, the Lagrange equations. Actually, the concept is very easy. Pretty sure no one is equations. Basically, the idea is I have to evaluate how a particle, actually a group of particles, are moved in a fluid. That means we have to know the characteristics of how the fluid is moving. Basically, is what here is represented by the variable u. That of course is vectorial, is three-dimensional. The transport is pretty easy because we have that the position of new particle starts from the position of the previous position plus the movement and plus a random part. This random part is distributed with average with 0 and sigma. Evaluated as in the formula. A key is a coefficient of diffusion, basically something related how the fluid make diffuse the particles. And the last equation means that this value is related with the depth. The value of the diffusion is related with temperature, and we are lucky because ROMs produce as output this value. So to run Wacom, we need the sewer outlets, basically the source of emission. Then we need the results of ROMs, and we have everything we need to study how the particle emitted by the material source moves and diffuse. And this is a kind of out of input and output we can expect. These are real values from the simulation over the Campania region and beyond Naples, and some details. The details are just zooms because the resolution is so high, it's 140 meters, so we can even zoom without losing information. Yes, we need, actually for this kind of say, we use, okay, this is really spoiler alert, we use the outputs of this model to feed another model that is an AI-based model, and we should have 80 meters resolution to have the best results, but it will be in the next. This is the architecture of Wacom. This is very important because if you understand how the computation is distributed in different parts, different components of the Wacom, you understand why we choose this model to try to apply in the malleability, the computational malleability, because here we have three sides. One side is the outer side. Basically, it's something that is repeated each simulation time. That usually is 1 hour. Then we have another cycle that is the particle size. The particle size could be definitely parallelized because all the particles can be moved in the same time. As I told you before, no one interaction between particles. And finally, inner cycle. The inner cycle is how the particle is moved during the simulation time, actually the integration time, the delta t you saw in the formula in the previous slide. And that means, yes, we can approach the parallelization, the hierarchical parallelization in a really classical way. It means defining in advance the number of resources on which we parallelize the computation, but then we can do even more, and this will be in on the next slides. Now, this is the parallelization schema. These are really full-fledged schema with 3 levels of hierarchical parallelization. We have distributed memory between processes, shared memory between threads, and if we have GPUs or multiple GPUs, we distribute even with multiple GPUs. Then I will show you the results with multiple GPUs are impressive. Yes. Because without evaluation, we cannot sell what we do. So this is our toy machine, basically a machine that has 20, it's strange for me saying these numbers here in the Barcelona supercomputer, but anyway, as a 256 cores total in 480 nodes. 4 nodes are only computing nodes, regular computing nodes. The other 4 nodes has each one for a P100. No, V1. It's there. Which how I spend my money here, right? Anyway, it's V100, V100. And for a total amount of GPU cores of more than 81,000 that could be sold to muggles, because it's a really big number for muggles. Okay, I'm scared by the machine behind me, but anyway, it's fine. The test is very simple, only 24 simulation hours, and how many particles? Oh, yeah, and this is interesting. During, basically, we simulate, or let's say an oil spill. Let's imagine an accident. And immediately we spill 25 millions of something in the sea. And we want only one at time 0 in a place. And we want to know where this something is moving. That actually we can define this model even how is this something, for example, sync or don't sync. For example, I could use this model to trace wrecks or human bodies. We did it, the tales of life. We tried any possible combination. The baseline is all sequential as usual, and then we tried with just distributed memory, shared memory, distributed memory, and shared memory, and then with the GPUs and without GPUs. You can use the slides to get details about this, but I'm very happy to show these results that are interesting. Even the chip run means without GPUs. We have an incredible speed up. In the next slide, we have the speed up. But what is really incredible is what happens with using the complete hierarchical stack, basically using the distributed memory, the shared memory, and the GPUs. Basically, this is the speed up, and that's incredible. What happens? Basically, we tried even to run simulation by billions of particles. that we cannot host in production, but we can do it as a scenario analysis. And it's incredible. I'm really happy about this model. Yeah, malleability. Malleability is the magic word of Admire. We learned that is not good for all recipes, but for some recipes it's super tasty, as in this case. Because I have to remember you that we have three cycles, and one cycle is basically the outer cycle. It's repeated basically independently by the other one. This means we can enlarge or shrink the number of processors and then let distribute things. But we need only a magic wand to do that, and this magic wand is called the Flex MPI. We did basically almost at the beginning of the project, we did a kind of mock-up written in C to understand immediately if it was feasible or not. It was super amazing. We worked together in co-design with the Flex MPI team, and finally we had miracles. Maybe more than miracles, magic stuff. We have three main cycles, and this is exactly the same kind of computing model, programming model of Flex MPI, because Wacom was designed with malleability in mind from scratch. And just, okay, this is the typical way how Flex MPI is implemented, and you can trust me, is exactly what we did with Wacom and Refil. If you don't believe, of course, there is the public repository, and I invite you to try all possible flavor, and this is important. Malleability is one production flavor, it's not experimental. The only thing you need is access to the Admire version of Flex MPI, and as Flex MPI will be connected with the intelligent controller, it will work. Just to test, this test is pretty famous. Basically, we increased the number of processors at each simulation hour, and we want to show that a metric that is basically the number of particles computed in a unit of time is almost constant. Actually, here the metric is the dashed line appears to be decreasing just because the proportions are not good. If you consider the right proportion, is almost constant, but it's only one scenario. This most useful scenario is this one. Basically, here we set the metric, and we want to increase and decrease the number of processors to almost fit the metrics. And even here, we have interesting results. Of course, when use this kind of approach, and as we discussed, matching malleable and not malleable resources is tricky. I imagine this kind of approach is perfect if I have, as in my case, a dedicated machine for this kind of application. And of course, we just talking together, we had some ideas about a future kind of scheduler for malleability. And I have to take together, and I was almost on time. I think I will be out of just 1 minute and a half, probably. We developed from scratch, yes, another workflow engine. Why? First of all, why not? Then, because environmental applications are really scaring application if managed at scale, because we have a legacy software that we cannot touch. We have to run in a sandbox. Each software could be just a simple Python script or a huge parallel model, like, for example, but it's not only the only example word for ROMs that are really resource hungry, and everything have to be designed in the easiest way possible. And usually these stuff are not designed to work together. You need adapters between the models, they usually use the files to communicate each other. And of course, we developed from scratch another workflow engine. The name is Dagon Star. The star is for anything. Okay, Dagon is kind of Aquaman or from Phoenix. It's very easy. super easy. If someone thinks that is similar to parcel, yeah, she or he is perfectly right. If someone thinks that is similar to StreamFlow, yes, again, it's perfectly right. No one of us copied each other. It's culture, more like a stream. Either Python script is possible web integration and is designed for this kind of application when we have blocks that are legacy that have communicate each other. The nice thing that we can run each block everywhere we want, and all the data staging is completely automatically and transparent. Yes, we are studying to introduce other kind of communication over the SSH or as secret copy or grid FTP or some other stuff are kind of modern workflow behavior. How to define a workflow? We don't use scripting languages, we use Python, and we use a nice way called something that we call nice way, of course, because it's how it's that's all, so it's nice. It's called the workflow schema. Basically, in the workflow schema, I refer the data stream is automatically inferred by defining for each task the relation specifying the files as imagine all the tasks to share the same file system. But of course, it's not mandatory. It's not like Galaxy workflow engine that needs tasks to share the same file system. This is a kind of a shared file system, but could not be a shared file system. Just the references are shared. And this is called the workflow schema. Once in a review, once complained that workflow // was not registered on the internet. I did answer just to be polite. And the syntax is the name of the workflow, because we can do even a workflow transversal. That means different workflows can interact each other at the same time. Then the name, the unique name of the task, and then everything is referred to the scratch directory of the task. Of course, security is not considered, as almost everything we did. Then, as you know, everything has a start, sooner or later comes to end. And maybe it's not the end, every end is a new start, but we're so, okay, by the way, I could really last forever on this application, so I want just to stop. And everything is available on GitHub, and for each GitHub repository related to the environmental application, there is the example directory. The example directory, there are tutorials. We are really focused on this reproducibility and didactic and teaching about this stuff, because we need new people. Actually, is the usual joke about the candy with some really attractive that is give for free, and we want to give the candy, and we have even the cookies. Then oh yes, how is possible to run the environmental application? This is important. Could be done as examples on the DagonStar repositories. It's possible to run, or there are actually instruction to run a fake version of the environmental application. Basically, is a dry run. Everything is exactly the same as the real case, but data are pre-computed. Otherwise, you test the models, you don't test the application. And otherwise, there are also the instruction to compile everything, whatever. Then you can run on the Torino cluster, and then of course you can use the application that is running operationally on our premises. For Wacom++, there are a couple of tutorials to run both no malleable and malleable version. Finally, it's almost file safe. The application once suffered a really catastrophic event. When I say really catastrophic event, you know, American movies Yes, that's kind completely destruction of a storage. And basically the users never felt that something was wrong. Okay, my weekend, yes, of course. But in less than 72 hours, everything was up and running. No one was affected. And it was really a great satisfaction when someone asked me, and you don't, Roberta told me, you don't have the backup, isn't it? I thought, no, I have everything. So, yeah, finish it. If you have questions, yes, I ran out 3 minutes and 45 seconds. I suppose I have tons of questions. And I huge amount of questions from all the BSc.
I have a question.
Okay, I'm scared now.
How we can integrate the Adobe file system with Capio in your?
Okay, this is a great spoiler because I'm working on it at design level. Means, okay, I understand how
It
it
would be a very good use case for the users and also for us to see that everything is working together.
Yeah, basically, what I'm thinking, okay, I didn't forget to mention, I did it by purpose. The presentation is full with the skipped slides that I didn't show you, but the Dagon is completely modular. The stager could be changed as you want, and you can have a multiple instance of the stager component at the same time. That means, for example, I can use to communicate. For example, well, I can stage data to components running on a cluster far away with the grid FTP, and then use, for example, Hercules or Capio-based staging on an internal cluster. Basically, it's possible because with Capio, the idea is this one, but please, this is really a spoiler. In the workflow description, made basically using the workflow schema, theoretically, I have everything to automatically generate the JSON file that are the configuration for Capio. And if this is working, it's straightforward having a plugin that runs Capio and the Dagonstar. Dagonstar is really modular. For example, during supercomputing, just exchanging few messages with Dante, we thought, okay, let's use proxy store to change to, and proxy store is used in different kind of scenarios. It's basically the opposite problem. It's moving data between the great distances. So it's definitely possible, and I don't know if I can convince people to work on the integration of Capio and Dagon in these months. I really hope yes, because in this month, technically it's month. Technically it's month. It's 1 month. That is unfeasible. Of course, probably for if we have the extension for March, could be feasible. Because just even talking with Massimo, yes, the approach could be feasible. There's everything in the workflow schema that could be used to create automatically the Capio connectivity.
Okay. Thank you.
You're welcome.
So who's next?
Please, Barbara.
Barbara.
Yes, the last one.